This video will explain the Thorium Molten Salt Reactor, or TMSR, a new kind of nuclear reactor that will solve humanity's energy problems. The best way to understand thorium molten salt reactors is to compare them to light water reactors, or LWR. Light water reactors use solid nuclear fuel. Fuel rods are filled with uranium pellets and are bundled together to form fuel assemblies, which are stored within the reactor pressure vessel. Water is used as both coolant and moderator. Water is also turned into vapor, boiled within the reactor at temperatures of about 300 degrees, which turns a turbine to generate electricity. Because the fission products, or FP, that absorb the neutrons are contained within the fuel rods, fission products increase in quantity as more neutrons are absorbed. Light water reactors require high concentrations of uranium to increase the reactivity inside the reactor during the early stages of operation, and excess neutrons are absorbed by control rods. The reactor is designed to maintain a proper critical state at all times by adjusting neutron absorption as FP and the amount of neutrons increase. This means that it is necessary to maintain delicate control of the reaction, which means that the interior of the reactor pressure vessel needs to have a complex structure, with various devices including many different types of control rod. In contrast to this, thorium molten salt reactors use a liquid fuel made from molten salt mixed with thorium and uranium fluoride. The molten salt in the reactor core transfers heat to the secondary coolant in the primary heat exchanger. The secondary coolant then generates steam in the steam generator. This steam turns a turbine to generate electricity. The core inside the reactor vessel uses graphite as a moderator instead of water. Because TMSRs are liquid fuel reactors, there is no need for complex control using control rods. The reactor vessel has a simple structure consisting of only the fuel salt, a few control rods, and the graphite moderator and reflector. Light water reactors and thorium molten salt reactors use different nuclear fuels and have slightly different nuclear reactions. In light water reactors, slower thermal neutrons are more likely to cause nuclear fission in uranium than fast neutrons, so the speed of the neutrons is decreased using water as a moderator. Nuclear fission occurs when neutrons collide with uranium molecules, resulting in fission products, or FP, and usually two more neutrons. One of these two neutrons will then collide with a new uranium molecule, once again giving rise to nuclear fission and continuing the chain reaction. With nuclear bombs, the other neutron also causes a chain reaction, which expands explosively and instantly generates an enormous amount of energy. Light water reactors suppress this explosive chain reaction by mixing into the fuel large quantities of uranium-238, which absorbs the excess neutrons and thereby transforms into plutonium-239. Combustion with the solid fuel used in light water reactors is uneven. As such, the reactor must be shut down around once per year in order to change the position of the fuel assembly and ensure homogeneous combustion. Finally, gaseous fission products such as krypton and xenon get trapped and build up within the cladding of the fuel rods, so it is necessary to replace the fuel rods every 3 years in order to prevent internal pressure from damaging the rods. Thorium molten salt reactors use nearly the exact same nuclear reaction as light water reactors, but use thorium instead of uranium-238 to absorb excess neutrons. Because there is no uranium-238, plutonium is almost never produced. The thorium that absorbs the excess neutrons has a half-life of 27 days and transforms into the same uranium-233 that is used as a nuclear fuel. In this way, nuclear fuel is replenished and the reactor becomes almost self-sufficient. Uneven combustion does not occur because the liquid fuel salt used in thorium molten salt reactors can be constantly circulated and stirred in order to maintain a uniform state. Moreover, gaseous fission products are constantly removed, so there is no need to replace the fuel. When loaded, the fuel-salt composition ratio is only 0.3% uranium, 12% thorium, with the remainder being molten salt. Even after the reactor becomes operational, the amount of uranium is self-sufficient and almost doesn't change. FP is produced as thorium is consumed. The efficiency of the reaction decreases because of this FP. Because of this, chemical treatment is required once every few years to remove FP and replenish the thorium. This returns the reactor to almost the same composition ratio as when the fuel was originally loaded. In the end, there is only a very small quantity of FP to be disposed of, and very little waste from spent nuclear fuel. Because light water reactors use water for cooling, the pressure inside the reactor vessel can be as high as 70 atmospheres. This means that the possibility of a steam explosion cannot be ruled out. Thorium molten salt reactors, by contrast, operate at normal pressure, so there is no risk of accidents associated with high pressure. LWR also comes with the risk of explosion due to hydrogen generated in thermochemical reactions between the fuel rod cladding material and water. This occurred in the Fukushima nuclear accident. With TMSR, however, such thermochemical reactions do not occur. With LWR, there is also the risk of reactor core meltdown if problems occur during the cooling of the decay heat after reactor shutdown. This also occurred in the Fukushima accident. With TMSR, however, the reactor core is already molten, so core meltdown does not occur. Even if there were an abnormal temperature rise, there would be no serious accident as the properties of the liquid fuel would remain the same. After the nuclear accident at Fukushima, safer light water reactors, such as SMR and next-generation light water reactors, have been developed. However, the above safety concerns have not been entirely eliminated. With TMSR, by contrast, even if something does go wrong and the control rods are unable to shut down the reactor, it is possible to simply discharge the fuel salt into a drain tank directly below the reactor. This will shut down the reactor, and re-criticality does not occur in the drain tank because there is no moderator present. In short, thorium molten salt reactors have double and triple safety measures in place, which makes it impossible for severe accidents to occur. In the spent nuclear fuel generated from nuclear reactors which use solid low-enriched uranium, such as LWR, there is still about 1% of fissile uranium-235 and plutonium-239, and a large amount of uranium-238, about 95%. These must be reprocessed and reused as MOX fuel or sent away for final disposal. If the plutonium produced during the operation of a light water reactor is kept and not reused as nuclear fuel, there is the concern that this plutonium could be used for nuclear weapons. This raises the issue of nuclear weapons proliferation. In contrast to this, with TMSR, chemical treatment is performed once every few years to remove fission products from the fuel salt. However, because these reactors operate continuously for long periods of time and use up the nuclear fuel, there will never be a large buildup of spent nuclear fuel. Moreover, with TMSR, uranium-238 is not used as nuclear fuel, so in principle almost no transuranium elements are produced, including plutonium. Because of this, the amount of high-level nuclear waste produced by TMSR is extremely small. Finally, TMSR can use plutonium as an alternative fuel to uranium-233. This means that the plutonium produced by existing nuclear power plants can also be consumed in a way that is vastly more efficient than burning MOX fuel in plu-thermal reactors. TMSR can also use as fuel large volumes of fissile isotopes of transuranic elements. So the development of TMSR will enable humanity to solve the problem of spent nuclear fuel, nuclear waste, and also nuclear proliferation. What is the cost of power generation in TMSR compared to other methods of power generation? Based on the conceptual design of the Mini Fuji 2 25 megawatt reactor, the estimated cost of power generation would be around 6 Japanese yen per kilowatt hour. For the Fuji 200 megawatt reactor, the estimated cost would be around 5 Japanese yen per kilowatt hour. Even compared to the cheapest light water reactors, these costs are overwhelmingly low. Why are the costs of power generation so low with TMSR? The first reason has to do with fuel costs. TMSR uses low-cost thorium as nuclear fuel. Moreover, unlike light water reactors, TMSR does not leave any nuclear fuel unused, using the exact amount of nuclear fuel that is necessary. In addition, there is no need to process nuclear fuel into complex nuclear fuel assemblies, so fuel costs can be kept very low. The second reason has to do with the costs of waste disposal. Since TMSR does not produce unburned spent nuclear fuel, they produce only about 1/1000th of the high-level nuclear waste compared to LWR. As such, the costs associated with reprocessing and waste disposal are very low. The third reason is that TMSR does not need to change fuel as frequently as LWR, which means that they can operate continuously for long periods of time and achieve high rates of operational efficiency. The fourth reason is that the reactor's structure and control mechanisms are simple, which means that construction and operating costs can be kept down. The amount of fuel necessary to operate a 1 million kilowatt power plant for 1 year depends on the type of fuel. For thermal power generation using fossil fuels, the amount of natural gas required is enormous, 950 kilotons. A light water nuclear reactor requires 21 tons of enriched uranium. With TMSR, by contrast, the same amount of energy can be produced using only 0.7 to 1 ton of thorium. As such, approximately 80 to 115 tons of thorium would be enough to meet Japan's electricity demands for 1 year, and a stockpile of just 1,000 tons, which would be less than 100 cubic meters in volume, could meet 10 years of electricity demand. Furthermore, since the amount of thorium required per unit of electricity is so small, it is possible to stockpile it for decades. In short, a successfully developed TMSR would mean no further need to worry about securing energy supplies, even if it becomes difficult to import fossil fuels in the event of an emergency. TMSR can produce CO2-free hydrogen at a low cost of about 20 Japanese yen per cubic meter by using the heat and electricity generated by its power plant. In addition, renewable energy such as solar power often generate more power than demand during the day, but are unable to generate power during the night. At present, this gap between supply and demand is addressed at night by pumped storage power generation and by adjusting the output of thermal power generation. During the day, the excess power is often discarded. With TMSR, output can be adjusted according to demand. So instead of closing the gap between supply and demand using thermal power plants that emit CO2, TMSR is perfectly suited to supply flexible power generation to supplement renewable energy sources. Since the Fukushima nuclear disaster brought issues of safety to the fore, attention has been increasingly focused on the problems associated with nuclear power generation, such as spent nuclear fuel, nuclear waste, and the creation of plutonium. In Japan, with the restart of nuclear power plants delayed due to increased safety measures, there is now an increased dependence on thermal power generation. This has led to a rise in the cost of electricity. Thermal power generation now accounts for the majority of the electricity supply. However, thermal power emits large amounts of CO2 and also depends on fossil fuel imports, which means that there are concerns about the vulnerability of the energy supply in emergencies. On the other hand, the power output of renewable energy sources often fluctuates depending on weather conditions, and renewable power plants also require large land area. So in countries where the weather conditions are not suitable or where the land area is small, there will be limits to the amount of electricity that such sources can supply. The reality is that there is no solution to these problems, at least if the situation remains as is. However, the development of TMSR will fundamentally solve these energy problems. With TMSR, serious accidents cannot occur, and high-level nuclear waste is reduced. Moreover, instead of creating plutonium, plutonium can be destroyed. TMSR, therefore, produces extremely cheap electricity, providing CO2-free power without relying on fossil fuels. Moreover, by stockpiling thorium, energy can be secured to last for several decades into the future. The heat and electricity produced can also be used to produce low-cost CO2-free hydrogen, and TMSR can also supplement the fluctuations of renewable energy sources to produce a more stable electricity supply. Finally, the land area required for a TMSR power plant is more compact than the area required for an LWR plant. As such, there will be fewer restrictions on location and no limit to the amount of power that can be supplied. Why, despite these incredible features, has nobody yet bothered to develop a thorium molten salt reactor? In the United States, beginning in 1965, Oak Ridge National Laboratory operated MSRE, an experimental molten salt reactor, for 4 years without any serious accidents. In 1971, the conceptual design and basic technology was established for MSBR, a molten salt breeder reactor. However, during the Cold War between the United States and the Soviet Union, thorium molten salt reactors, which could not produce plutonium, were not considered useful by the US Navy, which was a major player in the nuclear arms race. As such, further development was blocked due to politics. Now, however, times have changed, and this technology has been reconsidered. TMSR is now seen as a solution to our energy problems, and dozens of venture companies around the world are currently working hard to develop a commercially viable reactor by 2030. Thank you for watching.